Now we will, for the first time, derive an expression for the electric potential that is generated by a source, which is, in this case, the point charges. This is the simplest, and this will form the basis for finding the electric potential for other distributions. So we will be considering a point charge, and we will find an expression for the potential generated by this point charge, treated as a source charge in the whole space. And you will see that it's indeed a function of space. So to do this, we consider first a source charge plus Q, and the electric field of this charge is, as we all know, at any point the electric field is always radial and outwards. Okay, so at this point the electric field in this direction, at this point electric field in this direction, and so on and so on. And this electric field drops as 1 over r square. So the further you are, the smaller is the electric field. Now there is another point B here, which didn't appear in the slide here due to the screen, and we, in order to find the electric field, the potential of this Q, we first find the potential difference between point A in the field of this positive charge Q and point B somewhere here. So we want to find the potential difference as we go from point A to point B. Now the result is as follows. I will show the details just in a moment, but first I will state the result and I will analyze this result. The result is that this point B here is here. So this is RB, this is RA. Okay, this is the position of the point A, and this is the vector that gives the position of point A. So it is at a distance A. RA is this distance, and the other point is here, and this RB is the vector that goes from Q to this point B, and the length of this vector is RB. The result says that the potential difference between this point in space and this point in space, due to the electric field that is generated by Q. Okay, so Q is the source charge that generates the field and so generates the potential. The potential difference between these 2 points in the field of the source charge, the source point charge Q, is given by KQ over RB minus KQ over RA. So V at B is KQ over B, V at A is KQ over A. Okay, so this is, we can think of it this way. Now take your A, take this to be at infinity, send this to infinity, so that RA becomes infinity, and let B here, instead of saying that this is RB, let it be any R, a general point. So in this case, this thing drops, and you get the potential due a point charge at some point R is given by this expression with the potential with respect to potential 0 at infinity. So this is the potential of a source charge, which is a single point charge of magnitude Q. Okay, and this is a very simple expression. As you can see, it says just K multiplied by Q here, divide by R. So whenever you put a source charge in the space, then the potential, the area, the region around the space where you have electric field now, and we know the expression for the electric field, has now potential. That is, it has energy tariff per energy tariff, which, and so this is the potential. It is a function of R, so as you can see, it varies with R, and at any R, at any distance R from the point charge, it is given by this simple expression, as you can see. Q here is to be substituted with its sign. So if it's positive, then the potential would be positive in the space. If it's negative, the potential is negative. This expression is true under this assumption that I am measuring here the potential of any point in space with respect to infinity, where I'm taking the potential by convention to be 0 at infinity. This is similar to, choosing the potential energy, the zero of the potential in a gravitational field. When we calculate the potential energy, gravitational potential energy, we take u equals 0 wherever you like, and you measure the distance from there. So it is actually choosing what is the zero of the potential energy there. Here, I choose the zero of the potential to be at infinity. When infinity, of course, means for a point charge at points very far, so that the field of that point charge at that point is 0. So this is the meaning of infinity in this case. Now let's look at the details, how we got to this result. Well, these are the 2 points. Now they are clear here. This is point A, this is point B, as you can see. And I want to find the potential difference between A and B. I use this formula, the standard formula, and the minus sign comes from the definition. I find this integral as I go from A to B through any path, because this is path independent. Take any path and divide this path into ds. I know what is the electric field. It's always radial outward. So consider this ds, for example. The electric field is along this r hat here, and this is ds. There is an angle between them. This is the expression of the electric field at this point here. As you can see, it's along r hat. This should be r hat, by the way. It's not the vector r. It's the r hat here, unit vector. Now, E dot ds is r hat reduces to r hat dot ds. R hat dot ds is modulus r hat modulus ds cosine theta. Modulus r hat is what? Is 1, because it's a unit vector. So this reduces to ds cosine theta. R dot ds cosine theta. Okay? ds cosine theta. But what is ds cosine theta? ds cosine theta is the component of ds along r hat. But what is this? This is dr, the increment in along, and the change in the r along the r direction, the radial direction. Okay? And therefore, E dot ds reduces to kqr squared dr. So this is the dr. Now, the integral, therefore, when you substitute here, r dot ds instead of r dot ds, you substitute dr, then inside you will have kq over r squared dr. And you take kq outside, it becomes dr over r squared, and this is integral over dr. Now dr here, now you don't have vectors anymore, which means I am integrating over length. So I start at this r here and end up with this r here. So this r here is this length r, not a vector, and here it is the length of this vector. So r is this distance from here to here, okay? Because the variation is along dr, so actually it says that the limits of integral, so this distance, this length, and the other is this length here. So I substitute RA, RB, not vectors now, just length. And when you integrate, the integral of 1 over r squared is minus 1 over r. Substitute, you get this expression that we have just obtained. And then when you set, you take this to go to infinity, then this term becomes 0, and this is the expression that we get for the electric potential of a point charge. This is the result that I have derived. These are just the details of the derivation. So that's it. This is my expression. And what does this mean? What does this mean? What is the physical interpretation of this? Now, the meaning of this expression is the following. The physical interpretation of the potential at this point is the following. Let me just show it here. Now, this is my point charge Q here, can be positive. This is the potential, this is point R. So this is V of R. What does the potential, which is KQ over R, what does this mean? That the potential at this point here, due to this point charge, is V of R. Now, you remember, it means the following. Now, we know that delta U is equal Q naught delta V. And therefore, delta V is equal Q naught, sorry, is equal delta U over Q naught. That is, the potential difference is just the potential energy per unit charge. Now assume you take a Q naught here at infinity. You are at infinity and you take a test charge, Q naught. Now bring this test charge from infinity to this point here. Okay? Now the change in the potential energy of the two charge system, the source charge and this charge, is delta U, and this is equal W external. This is our general result. The change in the potential energy of these two charge system is equal to the external work done by an external force to bring this charge from this initial position to final position. The initial position, I take it at infinity, and I bring it to this position R. Now, this external work does work in a manner that does not change the potential, the kinetic energy of this point charge. So if there is no change in the kinetic energy of this point charge as it comes here. So if it was at rest here, if it were at rest at infinity, I bring it very slowly so that it's still at rest here when I bring it to this point. Under this condition, this is true. Now, what is delta V? Delta V is delta U divided by Q naught, which is delta, which is W external by Q naught. Therefore, but what is this? Now, delta V in this case is the external work that per unit charge, because you are dividing by Q naught. So when you divide the work by Q naught, you are finding the work per unit charge. So this is the work done by external force to bring the this test charge from infinity to this particular point. Now, delta V is V at infinity minus V at R minus V at infinity. But V at infinity is 0, so delta V reduces to V. So V of R is this. So V of R is actually the external work done by the work done by an external force to bring test charge from infinity to the point R per unit charge. Okay, so this is the meaning of this statement, and this is how we need to understand the electric potential at a given point in space due to a point charge. When you bring the work done by an external force to bring a test charge from infinity to that point R here, per unit charge, that work per unit charge is actually this potential. Why is this important? This is important when we consider the potential energy of a system of point charges. This concept is crucial to understand what does this mean. Now, in this expression, this is just, I iterate what I have said, you substitute always the source charge here with its sign. Now, plotting of the 3D plot of the potential function of a point charge is this. You know, the charge is somewhere here, and so this is how the potential changes. It's highest, as you can see here. So the vertical axis is the value of the potential. It's highest near the charge, and it drops, becomes smaller as you go away from the charge. And this drop is shown by this line here. Try this important checkpoint before you proceed, please. Now we consider the electric potential energy due to point charges. So we have defined the potential of a single point charge, which is possible because to define the potential, you need only a single charge because the potential is due to the results because you have the field generated by this source charge. But if you want to define a potential energy, then in this case you need at least one more charge so that you have a system of two charges. And this is what we will be doing now. We will be considering a system of 2-point charges, which is the simplest possible system, and we will see how we can define the potential energy of this two-charge system. Now, to do this, to define the potential energy of two-charge system, we consider the process of assembling the charges. In other words, I have a charge here in a single point charge Q1, for example, okay, and it has its own potential in the whole space, and I want to bring another point charge and put it at P. Okay, so originally at point P there is no other charge, but there is the potential. The potential of Q1 at P is this, KQ1 over R12, just what we have learned. R12 is the distance from this point to this point P, and the 2 is because we are going to bring charge 2 Q2 and put it here. Now, I bring another charge Q2 and put it here. Now bring it, what does it mean? It was not in the vicinity of Q1, so it was not feeling the field of Q1. It was not in the potential of field of Q1. It was means at infinity. So I bring that charge Q2 from infinity and bring it to this point P. Okay. Here in the figure it's shown as a negative charge, but the result in what I'm going to derive here, the result that I'm going to derive is independent of the sign of this charge. So bring a charge from infinity to this point here. Okay. Now, in doing so, you are bringing a charge from infinity to that point. Then there is an external agent bringing that charge to that point. So there is an external force doing work on the system of two charges. This is the source charge, and this is the test charge, if you like, that is being brought here. Okay, so this external force is doing work, and this work is equal now, as we have just learned, to the change in the potential energy of this two-charge system. So this is the relation, okay? Because Q2 is the charge that has been moved, and delta V is the change in the potential difference between these two. This quantity is what? Is delta U. This is delta U, okay? Because delta U is Q delta V, and this Q2 is the test charge, because the other charge Q1 is the source charge that is generating the potential. So the work done by the external force is equal to the delta U, which is the change in the potential energy, and the change in the potential energy is Q2 multiplied by delta V, which is the change in the potential. Potential of what? Of the 2 points where the movement of charge has been involved. The first point is at infinity, the other point is P. Okay? So delta V is the potential difference between this point P and infinity. But of course, keep in mind the potential at infinity, we took it as to be 0. So this change in the potential, which is equal to this and which is equal to this, and it is equal U at infinity, U at this point, minus 0. Why 0? Because, you know, delta, where did we start from? We start from infinity. At infinity, Q2 was not feeling the field of Q1, so there was no potential energy. It's just 0. And therefore, this is the change in potential. What is delta V? Delta V is V at this point minus V at infinity, but V at infinity is also 0. Therefore, this term is Q2. This is the potential due to Q1 at this point. Okay? If you just multiply these, you get this expression. That is the potential energy of these 2-point charges is equal by this, is equal to this expression. As you can see, it is K and multiplied by their product divided by the distance separating these 2-point charges. Again, these here, when you substitute them with their signs. And this is just a positive number because it is just a distance. So this is the potential energy of a system of 2-point charges calculated by taking the potential to be 0 at infinity. And it is at the same time, the interpretation of this is the work done by external force to bring the charge Q2 from infinity to this point. Now, one would say, okay, why should I not start with Q2 and then bring Q1 from infinity to this point? This is totally true, and this is totally legitimate question, and the result is definitely the same. So you can think of this as being the work done to bring to have Q1 already here and have its potential here, and bring the charge Q2 from infinity moving in the field and in the potential generated by Q1 to this point here. Or you can start with Q2 and with Q1 at infinity. Now the source charge becomes Q2, the test charge becomes Q1. You bring Q1 from infinity to this point, the result will be the same. The result will be the same. It will be a good exercise for you to try to rewrite the whole to derive that the result will be the same if you start with Q2 as your source charge and bring Q1 from infinity to this point. It will be a very constructive exercise actually to try to do that. So you might like to throw it. So this is the potential energy of a two-charge system, which is at the same time the work done by an external force to assemble these charges. This is the best way to put it, to assemble these two charges. Assembling these two charges means start with Q1, bring Q2 from infinity, or start from Q2 and bring Q1 from infinity. It is the same. What if I have now, what if I want to find the potential of a multiple point charges at some point? I mean, I have learned what is the potential of a single point charge. So if I had a single point charge here, Q, then the potential at any point, at a point P here, for example, distance R1, for example, here, was V1 was equal KQ over R1. Okay, this is what I have learned. Then what if I had another point charge Q2 and a third point charge Q3? Then what will be the potential, not the potential energy now, the potential of the system of 3-point charges Q1, Q2, Q3 at the point P? Now let this distance be R2, let this distance be R3. Okay, now we apply the principle of linear superposition that we have learned before, and says that the potential of, to find the potential here at point P due to these 3-point charges, you first find the potential of Q1 assuming that Q2, Q3 do not exist, then find the potential of Q2 assuming Q1, Q3 do not exist, then find the potential of Q3 assuming Q1, Q2 do not exist, and add them up linearly. Now since the potential is a scalar, then this addition will be a scalar addition. So therefore V in this case will be V1, V at P will be V1 plus V2 plus V3, and it will be K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3, which we write as sum in this case over I from 1 to 3 K Qi over Ri, which is just the expression that we have just considered. It is this expression. So this expression means this relation that I have just considered. And this is another example of superposition. The summation, again, keep in mind, this is just a scalar sum. These terms here, each of these terms here is a scalar, just a number, and it can be positive or negative depending on the sign of this Q. Okay, try to apply this to find the electric potential for an electric dipole. Now, what about the potential energy of multiple point charges? So if I have a system now not of 2 point charges, I have a system of 3 point charges. What is the potential energy of this system of 3 point charges? Now, well, we have found what was the potential energy of a system of 2 point charges, which was this. So when I have 2 point charges, the potential energy was simple. Okay, multiply them, k, multiply them, divide by their distance. So what if we have 3 point charges? Well, the formula is very simple. Actually, find the potential energy for each pair of charges and add them up. That's the formula. And it is, for example, for 3 point charges, it is this. So this is for the pair of charges Q1, Q2. This is the pair of charges Q1, Q3, Q2, Q3. When you add them up together, then this is the potential energy of a system of 3 charges. And what is this? This is the work done by external force to assemble the system of 3 charges. Okay, to assemble them, to bring them from infinity and put them in the spaces. In other words, this is equal to the work, or this is actually at the same time the change in the potential energy. But since the potential energy at infinity is 0, it becomes the potential energy. The change in the potential energy, when an external force, when you start with Q1, and then, for example, and then have an external force bringing first Q2 here, okay, in the field of Q1 to bring it to this position, and then have another external, after you fix Q2 here, you have external force bringing Q3 from infinity to this point. The sum of the work done by this external force in these 2 processes, okay, is equal to this expression. So this is the physical interpretation of the potential energy of a system of point charges. If you have more than 3 point charges, again, just apply the rule. Find the potential energy for each pair and then add them up. This is independent of the order of charges. That is, you can make this term here, put this term here. It doesn't make any difference. Okay. Try this checkpoint also before you proceed. Now, time for an example. And the example that we will be considered is actually about the potential and potential energy of a system of multiple point charges. So we start with a system which is composed of 2 charges. One of them is of magnitude 1 microcoulomb here, Q1, and the other of magnitude minus 4 microcoulomb. This is at the origin. This is at point 4 meters from the origin. I want to find what is the potential, not potential energy, of the system of 2 point charges at point P here. Well, it is just the formula that we have derived. You find the potential of each one of them and add them up. And the result is this. You sum from 1 to 2, so Q1 over R1 plus Q2 over R2. You substitute then these values, as you can see. Note that I have substituted Q2 with its sign. So this term is negative. Okay? And then if you add this up together and make the calculation, this is minus 4.2 kilovolts. Okay? So this is the potential of this 2 charge system at the point P. Now, the other question is how much work is required to bring a 3 microcoulomb point charge from infinity to the point P, and if this is done slowly so that the kinetic energy doesn't change. Okay? The kinetic energy of that point doesn't change. This is crucial to have W external equals delta U. Okay? Because if the kinetic energy changes, W external is not equal to delta U. W external is equal to delta U plus delta K. It's equal to delta E. So this is what I'm saying. I have a point at infinity. I bring it. It starts from 0. Then when it comes here, it's at rest. So there is no change in its kinetic energy. And I want to find how much work is required by an external force to do this. Well, the general rule is the work external is equal delta U, the change in the energy. And here, since the only energy that I have is mechanical energy, it's equal to delta K plus delta U. But since it starts at rest and ends at rest, or there is no change in kinetic energy, then delta K is equal to 0. So the W external is equal to delta U. Okay? This is just, I'm putting what I have been saying all the time into work in detail. So W external is equal to the change in the potential energy of the system. What system? The free charge system. Change from where to where? The change in the potential from when this was, change in potential energy. Potential energy between what configurations? The configuration when this was not there. What was the potential energy of the system of the three charges? Now the third charge is at infinity, so it doesn't contribute. So the potential energy of these two charge systems before, and then after this came in. So delta U in this case is the potential energy before this Q3 was in, and Q3 after the potential energy after Q3 was in, minus the potential energy before Q3 was in, when I had only Q1 and Q2. And this is equal Q3 times delta V. Delta V is what? Is the change in the potential between which 2 points? Your change in potential, you define it between 2 points. Which points? Well, the final point, which is P, and the initial point, which was at infinity, which is 0. So actually, it's Q3 multiplied by V at P. V due to what? V due, so this is what I'm saying. I'm saying 0. V due to what? V due to the remaining 2 point charges. Okay? So the potential Vp is the potential due to this point charge and this point charge at point P. And this is just what we have calculated in the first part, which is minus 4.2 times 10 to the power 3, multiplied by the point charge that you have brought in. It is a positive point charge, and therefore you substitute it as positive, and this external work is minus 1.26 times 10 to the power minus 2 joules. What does this mean? It means that this external force has to do negative work. Okay? So it takes potential energy from the system. And this means that the electric field, that is the work done by the electric field in this case, is positive, because it is the opposite of the work done by that external force. The meaning of this, of course, is the following, that this charge actually is pulled in by the electric field, and the external force is trying to keep this charge from accelerating because it's not changing its kinetic energy. So the external force did negative work because the charge is already going in and this is pulling it back, and so the work done by this external force is negative. This is the meaning of this negative work. Now, so this is the work, the external work done by the external force when this was brought in, and it is at the same time the change in the electric potential energy of the three charge system from the situation when this was at between the two situations when they are assembled, minus when we had only two and this was at infinity. Now find the total potential energy of the system of three charges. In this part, this is here. Now I want to find what is the total energy of the system of three charges. In other words, what is the total work done by external force to assemble these three charges? Start from Q1, for example, alone, then bring Q2 in, then bring Q3 in. This total work done by external force is the potential energy of these three system of 3 point charges. It is just, the formula is very easy, and you just substitute here. What remains is just enumerate it, and if you enumerate it in this case, then you get this expression, okay, and this is your answer.